All right, good morning again, Physics 30s. Mr. Thompson here. What we're doing is we're looking at page 57. We're working on Unit 3, Electromagnetism. We're just going to finish up this lesson on the force on a current-carrying wire in an external magnetic field. All right, question number 5. Wire carrying 7 amps of current is placed within an 85 millitesla magnetic field as shown. Determine the magnitude and direction of the magnetic force. Okay, so let's figure out the magnitude first. And so I write down my formula. Now, you'll notice the formula that they show here, right, is Fm. They have an absolute value around it, and they say that's L perpendicular, I, and B. And they put absolute value signs around the thing, okay? So that's the formula that they have. If you look on the top of page 55, okay? Now, they also use this idea of the vector notation. So like the force, magnetic force has a vector, and the magnetic field has a vector. Now, that's a little bit different than the formula sheet. The formula sheet has it just in a slightly different order. What they generally do is the same sort of thing for Fm, and then they call it I, L perpendicular, and then B. Okay? And so that's the version I'm typically familiar with. All right, anyways, let's just get our question done here. Okay? Of course, we have the wire. We have the strength of the magnetic field, the current, length. We're good. Let's plug everything in. We got 12 centimeters, 0.120 meters. Multiply that by 7 amps, and multiply that by 85.0 E negative 3 Teslas. All right, calculator time. All right, I get 7.14 times 10 to the negative 2 newtons. Now let's take a look and see if we can figure out the direction of this magnetic force. And so when I think about setting up my hand rule, I'm using my third hand rule for force. We're going to use our third left hand because it's an electron current, okay, going to the right. The magnetic field is shown with these little dots, so it's coming out of the page, all right? And so to set that one up, essentially what I'm doing is I'm pointing my fingers out of the page. My thumb should be pointing to the right, and therefore the force should go up in this direction here, okay? So the force is upwards on the wire, okay? Let me know if you have any concerns about that. What we did was we used the third, I call it the left-hand rule for force. All right, question number 6. All right, I put these ones on a separate page so we had a little bit extra room to work, and you probably want to use loose leaf if you're following along here. A wire has 9.8 times 10 to the 20 electrons traveling through it in 10.0 seconds. If it is inside a 37 millitesla perpendicular magnetic field, then it experiences a magnetic force of 6.1 E negative 2 newtons, and determine the length of the wire in the field. Answer in centimeters. Okay, so my formula. There it is. Okay, I'm going to solve this one for L perpendicular. That's going to be Fm over IB. Don't mind if I get rid of those absolute value signs, okay? And the vector notation. Forgive me. All right, the magnetic force. We have 6.10 E negative 2. And the current. Well, we have 9.8 E20 times 1.6 E negative 19. So that would be, in fact, our current, because it's the number of electrons times the charge on each electron. And then the magnetic field strength, okay? Pardon me, we need to divide that by time because it's Q over T. And then we multiply that by the 37 E negative 3 Teslas. Sorry, the fact of dividing it by the 10 is because I want to have current as charge over time, right? So I equals Q over T. And that's what the time factor is right here. Put in there, okay? No big deal. Quick little fix, we got it. All right, let's get our calculation done. right, I got decimal 105, and so it would be 10.5 centimeters. Okay? Moving along, question number 7. 60-gram wire that is 4.2 centimeters long is placed within an 800 millitesla perpendicular magnetic field. As shown, the electron flow through the wire is 11 amps. Determine the initial acceleration of the wire, assuming it is at rest if the electron flow goes from y to x. Or in part B, x to y. All right, so if it goes from y to x, that means essentially it's the electron flow is into the page. Okay, so here's y, here's x right there. It would be end up going into the page there. So let's take a look at how we'd apply our hand rule there. The hand rule, of course, would have the magnetic field going this direction. The thumb should go into the page, okay, for the current, which we would call the I for current, okay? And then the force should be upwards. Okay, and that's using what we call our third left-hand rule for force. Electrons, that's why we're using our left hand. All right, now that we know that the magnetic force is up, we know that the gravitational force is down. And so if we set up our net force, force is equal to the magnetic force going up plus the force due to gravity going down. Let's do the calculation right here. So I've got Fm is going to be L perpendicular times I times B. And so let's go ahead and put in our values there. So 4.2 centimeters times I, which is 11 amps, times 800 e negative 3. Then we're going to add to that the mass of it, which is 60 grams. Convert it to kilograms, and then we're going to need to multiply by negative 9.81.
Mr. Vandergreen and Ms. Johnson, we are waiting for you in the library for the Jersey meeting. John and Joanna, can you please come to the library?
Well, there's Mrs. Sechrist, if you haven't heard from her in a while. All right, let's get the calculation done. I get this number, negative 0.219 newtons. And so it's obviously 2.19 times 10 to the negative 1 newtons down. Now we know that the net force is equal to the mass times the acceleration. So the acceleration is going to be F net over m. And so negative 0.219 newtons divided by 60 e negative 3. I get negative 3.65 meters per second squared. All right, so now when we do the second part here, which is from x to y, what does that really do? Well, x to y is going to give us the following. The current is essentially going to be reversed, and therefore the force should be downward. The magnetic force is downward, gravity is downward, they both act downward. Okay? So now, both Fm and Fg act downwards. We can figure out the F net by going ahead and adding them together. So what I'm going to do is I'm just going to use the calculation from above. There's no sense of writing all those numbers out again. And instead of the negative, which I put in right here, okay, I'm just going to neglect that negative and keep it positive. So decimal 0.42 times 11 times 800 e negative 3, and then plus 60 e negative 3 times 9.81. Okay, so what I my calculation was punched in. I got the following: 0.9582 newtons. Again, same calculation as above, but without the negative 9.81. Just keep it positive and sum them up together. That means the acceleration is going to be F net over m, so divide it by 60 times 10 to the negative 3. Oops, sorry about my 2 there. What happened? And I get the following: 15.97, so 16.0 meters per second squared. All right. And then last one, question number 8. A Physics 30 student conducted an experiment with a current-carrying wire that is suspended inside of a magnetic field. She varied the mass of the wire inside the field and measured how much current was required to suspend the wire. All other variables were held constant. Sketch the straightened curve for this relationship, provide the equation of the straight line, determine the significance of the slope, and provide units for the slope. All right, the key idea here is that in the experiment, the wire is suspended, okay, inside a magnetic field. That means that there's two forces that are balanced: the force due to gravity and the magnetic force. Now, the equation for the magnetic force, as you've seen a few times in the past here, L perpendicular times I times B, okay? That's equal to M times G, where G is kind of the vector here, but there's an absolute value of that. Now, you can put absolute value around G or MG, either one's fine. All right, I'm going to drop out the vector signs here and the absolute value signs and kind of get to the answer here. So what am I going to do? Well, I need to sketch the straightened curve for the relationship. And so find out what your manipulated variable was in the responding variable. So manipulated variable is what? The mass of the wire. Now, what is the responding variable here? The current. It says here, right? Measured how much current was required to suspend the wire. Okay, so what we do is we take the relationship here and we solve it for the current, for I. So I have the following. I is going to be equal to M times G over L perpendicular times B. Okay, so to solve the question here, what we need to do is try and realize that this is directly related. The current's directly related to the mass involved. Okay? So we have the following. That gets I equals G over L perpendicular B. That all multiplied by M. This is kind of like your Y variable. This is like your slope. And this is going to be your X variable. And there shouldn't be any y-intercept. And so when you do your graph, it'll look like this. Mass will be along here, my manipulated variable. The current is the responding variable, and it should be a straight line relationship. Okay? Similar to that. Now, it also, in the question here, it says provide the units for the slope. So what are the units of the slope going to be here if we have G on the top, L perpendicular, and B on the bottom? Well, so the units of the slope are what? Well, G is meters per second squared, L is in meters, and B is in Teslas. Okay? So you have the following. 1 over, since mass cancels off, second squared times Teslas.